Good morning students. This is Navir Miravali. Welcome to online class of BSc first year, first semester mathematics class. Okay, in this video we are going to discuss about the partial differentiation. This is the first unit of first semester mathematics. So in this one, now we are going to discuss about the homogeneous functions and Euler's theorem on the homogeneous functions. Let's start the concept. Okay students, now homogeneous functions. What is that? Homogeneous functions. Homogeneous functions. So before going to homogeneous functions, I am going to write the some polynomials here. For example, 2x square. Suppose let us take the function 2x square minus 4xy plus 2y minus 5. Next one more is 4x square minus 10xy plus 5y square. If you seen this one, the first function f1. So let us take here 2x square minus 4xy plus 2y minus 5. So in this equation, if you observe that, how many variables are there here? Here two variables are there. So variables means here x and y are the variables. Here two variables are there in this one. So simply this is called the I have given a name f1 this one. So this meaning this is a function in x comma y. So the meaning of this one is the function of x comma y. This can be considered. Suppose next one, this is the function 2. In this one also this contains the two variables x and y. So that's why I have taken this is as the first function. So f1, this is as the second function f2. In both of these functions both of the functions contains the two variables here. How many variables are there? Two variables x and y. Our next concept is what is the degree? So how much the degree of this one? Here degree is degree. How much the degree? Degree is 2. Next one, here also this one also degree 2. If you observe that in the first one here, if you first one in this one, the first term, what will be the first term? 2x square. In this one you have to observe the what is the power of the variable. Here variable is the x square. So variable is the x. What is its power? 2. Coming to the second term, this is the x into y term here. So what is the variable powers here? So here variable powers means x power 1, y power 1. Now the summation of the variable powers, how much? This is also 2. In next one, if you see in here, what is the power of y here? Here power of y is 1. So in last term, what will be there? Minus 5 is there. In this one, what is the variable power here? So here it does not contain the variable. So hence its power should be 0. That means if you have to write the in terms of variable, you can keep it as x power 0 or y power 0 or x into y whole to the power of 0. So this is the power 0. So now our concept is you have to check whether all the powers of the term should be same or not. Okay, so if you observe that the first term contains the degree 2, this is the degree 2 here. Here also degree 2, but in the third term is degree 1. That means in the first one there will not have the equal powers and each and every term. Okay, so that means so such type of functions, if the powers in the all terms should be equal, then we say that such functions are called the homogeneous functions. Okay, here if you observe that here the powers of each and every term is not same here because of the first term degree is 2, second term degree is 2. That means how can you say that 2 here? Here the variables are x and y. Now x power 1 and y power 1 you can take. Now adding these two powers you will get the 2. So this is the second degree. The power of the second term is 2. In this one, the third term power is y power 1. That means, so the first two terms contains the degree powers 2, and third term contains the degree 1. So that means the first function does not have the same degree. So such type of functions are called the non-homogeneous. What is that? Non-homogeneous function. So if you observe, coming to the second function here, so what is the first term power here? First term is here x square. So the power is 2. In second term here x into y. So power means here x power 1 and y power 1. Now total degree is 2 here. Next one, in third term 5y square is there here. So variable is y. Now the power is 2 here. So if you observe that here, then you will get the powers same in each and every term. So every term contains the same power here. So such type of functions are called the homogeneous functions. Okay, homogeneous functions. How many variables in the both polynomials? Homogeneous functions in the variables x comma y and variables x comma y here. So I hope you understand the homogeneous functions of the two variables of degree 2. Okay students, this is the homogeneous function examples. Now we are going to write the homogeneous function definition. Okay students, now consider the function. Consider the function f of xy. Function means you have to write here two variables compulsorily, at least two variables. F of xy is equal to, so first I have taken degree x to the power of n. Next term can be written as x power. Now we are going to reduce the power of x and increase the power of y. Next term is x to the power of n minus 2, here y square. So plus and so on, you get a last term will be y power n. That means x to the power of 0 and y power n. Okay, so that is the concept here. Now here I am going to take here a naught, this is a1, this is a2, up to and so on, here a.n. Okay, so consider the polynomial f of xy is equal to a naught x power n, a1 x to the power of n minus 1 into y power 1, a2 into x to the power of n minus 2 y square, so on so on so on n, where consider this is equation 1. Okay, we see that this expansion f of xy, here f of xy is a polynomial in x and y. How many variables are there in x and y variable, such that the degree of each and every term will be the same. Okay, so that means here you have to write where is a polynomial in x comma y, in x and y variables, such that degree of each of the term is same. Which is, what is the degree? So first term degree is n, second term degree is n minus 1 plus 1. N minus 1 plus 1 means you will get the n answer. So that is, so every term contains the power same, so which is n. Okay, so that means such type of polynomials are called the, then we say that f of xy is a homogeneous polynomial in the variables x comma y of degree how much? Degree n. This is the general definition. But here we have to write here. If you taken here, what is the variables here? You have seen x to the power of n. Okay. So now in this one more definition in the degree concept, we have to write the definition of homogeneity applies to the polynomial functions only. Okay, we can apply the homogeneity to the polynomial functions only. To enlarge this concept, we can enlarge this concept. That means we can expand this concept of the homogeneity so as to bring even other functions within the scope. Okay, we say that the expansion in x and y is homogeneous of degree n. That means, so here we have to write the definition here. This is important one. The function f of xy is said to be homogeneous of degree n if f of xy can be written as, that means expressed as, x to the power of n into f of y by x. Okay, so that is, now this meaning is the function x comma y can be expressed as x to the power of n into f of y by x, meaning, so first you need to take the highest power of x. Okay, if you take an highest power of x common, now the function will be turned into the only y by x terms, not y, not x. Finally you will get the variable y by x term. So if you convert the f of xy in this form, x to the power of n into f of y by x, that is function in y by x, we will convert the given function in y by x term. You will say that that function is said to be the homogeneous function of degree n. This is the main definition of the homogeneous function definition. Okay, this can be used in the problematic. So before concept, the content which you have which I have explained here, this will be the, okay, this will be the, this will be the just explanation of the homogeneous function. But this one will be useful in the homogeneous function definition. So every function will be converted into x to the power of n into f of y by x. So here x to the power of n into f of y by x, here x power, what will be there? N. That will indicate the degree of the homogeneous functions. Okay students, I hope you understand the homogeneous function concept. This is the important definition what I have kept in the bracket box. Okay, that is the important one. Next one, some more examples. Suppose examples are, for example, here if you take in here a function f of xy is equal to root y plus root x by y plus x. If you see in here, now we are going to check whether it is the homogeneous function or not. Okay, for this one you have to do something here. First you have to take the given function and you can take the common of x to the power of highest power of x. So in the numerator what will be there? X power highest root x, that is the x power means x to the power of 1 by 2 here. So the highest power will be the only root x is there. So that's why we need to take the common root x. Whenever you have to take the root x, so in the first term what is that? Root y. In this one there is no root x term is there. Whenever you have to take the common, you will get here by root x plus second term is root x, already you have taken common. Next by here if you taken here x common in the denominator, highest power of x is x power 1, that is will be taken common. The first term does not contain the x, you can write the x in denominator and 1. So if you simplifying here, here what you have taken common, root x and x, both are the same variables, so that means both have the same power, same base. So if you expand this one like that, root x whole square you can write. Now square and root are cancelled, then you will get root of y by x plus 1 by x to the power of, that is root x into y by x plus 1. So in this one we can separate the x here, 1 by root x, so into y by x root plus 1 by y by x plus 1. So this is, so here you can write 1 by root x can be written as x to the power of minus 1 by 2. Now the remaining you have this one, this can be, if you observe that this one there is no x variable separately and also similarly y variable separately. So here just you seen here only y by x variable. So that means simply we can say that this can be taken as the function of, what is the variable you have seen, y by x, only y by x, not y not x, only here you can see y by x. So this can be converted in the form of x to the power of n into f of y by x, so which is homogeneous of degree n. N means what is that, minus 1 by 2 in the two variables x comma y. This is the checking of the homogeneous functions. Okay students, now we are going to apply the homogeneous function theorem, that means Euler's theorem on the homogeneous functions. Okay students, okay, now we are going to write the Euler's theorem of homogeneous functions. Okay, Euler's theorem on homogeneous functions. Homogeneous functions. So this is the very important theorem for the long answer type questions. This is the most important theorem. So now we are going to write the statement of homogeneous function. Okay, next statement. So this will be asked in the final examination. State and prove the Euler's theorem on the homogeneous function. First you need to write the statement. Okay, now the statement is, if z is equal to function of x comma y, so that means here given function of x comma y be a homogeneous function of x comma y of degree n, then you have to see that x into dou z by dou x plus y into dou z by dou y is equal to n into z for all x comma y belongs to the domain of the function. Domain of the function. This is the statement of the Euler's theorem. This is most important theorem for the public examination of Usmania University examination. Now we are going to write the proof of this theorem. Okay, now proof. Here. So if you first of all read the given theorem. If z is equal to f of x y be a homogeneous function of x comma y of degree n, that means here given z is a function, given that z is equal to f of x y will be given. This is what he is saying here, is a homogeneous homogeneous function of x comma y of degree also given here, of degree n here. So this will be given. Finally, what you have to show that, then we have to show that finally this one. So to prove this one, in this one what you have seen here, so on left hand side you can see here, this is, what is that, dou z by dou x will be there and dou z by dou y will be there. What you have seen, dou z by dou x, okay, so that is this one, dou z by dou x is there. Next one, what you have seen here also, dou z by dou y also you have seen here, okay. So you can see here dou z by dou x and dou z by dou y. That means, what is the meaning of dou z by dou x? Dou z by dou x means the partial derivative of z with respect to x. Dou z by dou y means the partial derivative of z with respect to y. This can be, you can find first of all. After finding these two things, you can write here by taking LHS side. What is that LHS side? This is the LHS side. If you take an LHS side, finally, if you simplifying, you will get n into z. So that is the procedure to prove this theorem. So this is the very simple method to prove this theorem. Okay, first what you have to find here, derivative of z with respect to x partially and derivative of z with respect to y partially. Okay, so for this one, what we have taken, z is equal to function in x and y. Function in x and y is a homogeneous function. Okay, already I have told you. So this is a homogeneous function. When a homogeneous function will be given, by the definition, the homogeneity is, this can be expressed in the form of x to the power of n into f of y by x. By using this one, so given function is homogeneous, hence z can be written as x to the power of n. Already degree will also given. Now that means x to the power of n into function of y by x. Okay, this is the definition, equation 1. Okay, now what you have to find here, now you are going to find the differentiating z with respect to x partially. So that means dou z by dou x, that is dou by dou x of x to the power of n into f of y by x. Okay, now this is dou z by dou x is equal to, so you are going to find the derivative of the function with respect to x. Here two functions are there, x power n into f of y by x. In both of the function, x variable is there. Okay, in x power 1 x variable is there and f of y by x, here also x term is there. So that means you can differentiating this one by using the u into v formula. So that means if you take an x power n as u, now u into derivative of function of y by x plus v into, v means second function f of y by x into derivative of x power n with respect to x. So now simplifying here, x to the power of n into derivative of this one. If you differentiating f, you will get f dash of y by x. Again you can differentiating internal function dou by dou x of y by x plus here f of y by x into, this will be derivative of x to the power of n with respect to x means n into x to the power of n minus 1. Now here finally x to the power of n into f dash of y by x into, if you differentiating y by x here, so in this one what will be the constant here? Here y will be the constant. Now remaining should be derivative of 1 by x. What is the derivative of 1 by x? Minus 1 by x square. Next plus f of y by x into n into x to the power of n minus 1. So first of all you have to write the positive term, that is n into second term. This will be the positive. So you have to write that one. So before writing that one, you should write the constant first of all, n into x to the power of n minus 1 into function of y by x. Okay, next second term will be here negative value is there, so hence you can write minus. So next one, x to the power of n is there, here x to the power of x, denominator x power 2 is there, so that means you can write x to the power of n minus 2 into y and f dash of y by x. Okay, this is the derivative of z with respect to x. Okay, this is the derivative of z with respect to x. Let it be equation number 2. Now we are going to differentiate here one again, this one. Okay, with respect to y partially. Okay, so I am going to take this one copy. Now the first equation can be differentiating here, differentiating 1 with respect to y partially. Now that means second equation, what first equation will be the this one. So in this one we can applying both sides partial derivative of y. We will get here, this is dou by dou y of z. Next here dou by dou y of this one. Okay, now if you differentiating carefully here, dou z by dou y is equal to, again here if you differentiate here, you are going to differentiating x to the power of n into f of y by x with respect to y here. So the term first one, what will be there, x to the power of n, that is the term without y, so treated as constant. Now dou by dou y of f of y by x. Okay, so taking x power n before. Now dou z by dou y is equal to x to the power of n into derivative of f means f dash of y by x. Now you can differentiating subfunction again. What is the subfunction you have? Y by x. Now simplifying here, x to the power of n into f dash of y by x into, if you differentiating here, sorry, here with respect to y here. So while you have to differentiating with respect to y, now denominator x, that is 1 by x is the constant. Now derivative of y with respect to y is 1. So finally you can get here x to the power of n here, 1 by x is there. If you simplifying that one, you can write here x to the power of n minus 1, x to the power of n minus 1 into f dash of y by x. Okay, this is the value you have seen. So what is the value? Dou z by dou y. So let it be equation number 3. So after finding dou z by dou x, this is the dou z by dou x. Next one, what will be there? Dou z by dou y you can find here. So after finding in the theorem, consider the LHS value. This is the LHS value. So if you taken this one, that means x into dou z by dou x plus y into dou z by dou y. Now taking here, consider x into dou z by dou x plus y into dou z by dou y is equal to, now you can write x into dou z by dou x. You are going to write the dou z by dou x answer here. So this is the answer of dou z by dou x. So taking properly here, so this value can be substituted in this one. So this is the dou z by dou x, and close the bracket, plus y into what will be there, dou z by dou y value. So this is the dou z by dou y value. Okay, now taking this one, and paste it. So this is the value. Okay, now simplifying here, that is multiplying x from this term to this term. So first of all, multiplying with first term, already x power n minus 1 is there, and whenever you have to multiplying, you will get x into n into x to the power of n minus 1 plus 1, that is n into function of y by x. Next minus, if you multiplying this one, x to the power of n minus 2 plus 1 will becomes n minus 1 into y and f dash of y by x. Next one plus x to the power of n minus 1 into y f dash of y by x. Okay, so if you observe that these both are the same terms, so this one and this one cancel. So now what you should get here, so finally you can get n into x to the power of n into f of y by x. Okay, look at here the first equation. What is the first equation? X to the power of n into f of y by x, that value should be z. Now you can substitute x to the power of n into f of y by x value here, n into this value becomes to the from equation 1 z. Okay, that is here z, this will be obtained since 1 from the first equation you can write here. So what you have observed here, what you have taken here, that is finally you can write, if you consider x into dou z by dou x plus y into dou z by dou y, you will get n into z, where z is, what is the z given in the problem? Homogeneous function. Okay students, I hope you understand this class. This is the very important theorem for the Euler's theorem, okay, for the homogeneous function only. So if you applying this theorem for a problem, in the given problem must be the homogeneous function. Okay, if it is the homogeneous function, then simply you can write, you can use this theorem. Okay students, okay students, now we are going to discuss about the another theorem for the homogeneous functions. Okay, so that is also second theorem for the Euler's second Euler theorem for the homogeneous function. Theorem 2, that is the theorem 1. This is also Euler's theorem for the homogeneous function, but here a quite difference is there. So that is if z is equal to f of xy is a homogeneous function of x comma y of degree n, then x square into dou square z by dou x square plus 2xy into dou square z by dou x dou y plus y square into dou square z by dou y square is equal to n into n minus 1 into z. Okay, n into n minus 1 into z. This is the theorem given. Okay students, now proof you are going to write. So first read the given theorem. If z is a homogeneous function of x comma y of degree n. So first of all we have to take, suppose z is equal to function of x comma y is a homogeneous function of x comma y of degree n. Okay, so just now we have explained Euler's theorem. What we say that by Euler's theorem. So here given function is the homogeneous function. Then what you have to write by Euler's theorem, x into dou z by dou x plus y into dou z by dou y is equal to n into z. Okay student, this will be obtained by the Euler's theorem. This is equation 1. Now by you taking this one, we can differentiating this one with respect to x, with respect to y. Why should we differentiating with respect to x and with respect to y? Now we are going to prove that this one, in this one, you can observe that here dou square z by dou x square is there. That means dou z by dou x, this is the first differentiating. If you differentiating with respect to x, you will get here dou square z by dou x square. So hence we can differentiating here with respect to x again. In the same way, we can differentiating with respect to y. You will get some equations. I can write here directly here. So differentiating with respect to x comma y, differentiating 1 with respect to x comma y partially respectively. That means first differentiating with respect to x, you will get one equation. After that, differentiating 1 with respect to y partially, you will get another equation. Here I am going to write the direct answers here. So you have to practice them. Okay. If you won't understand, then I will give the explanation in the classroom. Okay students. Now whenever you have to differentiating 1 with respect to x, you will get this answer dou z by plus x into dou square z by dou x square plus y into dou square z by dou x dou y is equal to n into dou z by dou x. So this is equation number 2. If you differentiating with respect to y partially, you can get here x into dou square z by dou y dou x plus dou z by dou y plus y into dou square z by dou y square is equal to n into dou z by dou y. Okay, you can get here another equation 3. So after that we can multiplying second equation by x and by y. Now multiplying 2 by x, 3 by y on both sides and adding them. Adding, we get directly this answer. What is that answer? X square into dou square z by dou x square plus 2xy into dou square z by dou x dou y plus y square into dou square z by dou y square is equal to n into n minus 1 into z. Okay student, this is the another theorem for the homogeneous function. Okay, I hope you understand this class. Okay, you have to note these two theorems on your notebook next video. Okay students, thank you.